So question 4 relies on the equation C equals Q over delta V. For scientific reasons that we do not have to get into and you're not responsible for, we are going to eliminate B as a possibility. It is not supposed to be a legitimate possibility, and we are going to analyze this question purely through the lens of math. So we know that the capacitance equals Q over V. So in this particular case, we are told that delta V is doubling. If delta V doubles, what would we expect to happen? So if you look at A, C, and D as our options, we can see that A is the only one which mathematically makes sense. If V doubles and C remains the same, then we would expect Q to also double. If you look at, so that makes A the correct one from a mathematical perspective. If you look at C and D, so the capacitance and charge cannot both fall to half of their initial values. If V doubles and Q is halved, the net result is that C would be reduced by a factor of 4, not 2. So that makes C incorrect from a mathematical perspective. If you look at D, if C and Q, if Q doubles and V is also doubles, we would expect C to remain the same. If Q goes from 1 to 2 and V goes from 1 to 2, then we now have 2 over 2. So that's the same thing as 1 over 1. 2 over 2 is the same thing as 1 over 1. So the capacitance and the charge cannot both double if V also doubles, making D also mathematically incorrect, making A the correct answer. Moving on to number 5, when resistors are connected in a series, which of the following would be the same for each resistor? The answer is current. That is just a concept. Again, if you think about resistors as traffic on a highway, or an accident on the highway, if there are 2 accidents on the same highway, then the second accident is going to cause traffic to slow down everywhere. It's not just going to be just around the accident where traffic slows down. Traffic jams can stretch for miles and miles and miles and miles. So as a result, whenever you have a single highway, the resistance affects the current everywhere, and as a result, the current is going to be the same everywhere. If you look at question 6, adding a resistor in parallel to a circuit, in fact, decreases the equivalent resistance. Just to give a very, very basic illustration of this particular point, you have a very, very basic circuit with a resistance of 2. So this is a circuit, and here's our little battery over here. So the equivalent resistance of the circuit is obviously 2 because there's only one resistor. We add another resistor over here with a resistance of 4. So if we want to calculate the equivalent resistance would be 1 over Req equals 1 over 2 plus 1 over 4. So 1 over Req equals 3 over 4, because 1 over 2 is 2 over 4. So if 1 over Req equals 3 over 4, that means Req equals 4 over 3, which is 1.33. So even though we added a resistor with a resistance of 4, the equivalent resistance went from 2 to 1.33. Whenever you add a resistor in parallel, that always decreases the equivalent resistance. Conceptually, the way you think about this is that if you add a highway, if you have one way to get from Teaneck into Manhattan, so there's going to be a certain amount of traffic on that route. If you add 2 ways, you can either take the George W. or the Holland Tunnel, even though both of those are going to have traffic on them, by definition, if you add a second way to get from point A to point B, that's going to decrease the overall traffic. This is the correct answer. C, decrease. Amazing. Moving on. Which of the following does not produce a magnetic field? So obviously a static magnet produces a magnetic field, and a current of magnets produces a magnetic field.
Please make your way to the front of the building. Your band is leaving shortly.
Fourth wall break. So a static magnet produces a magnetic field. That is just a magnet floating around, just chilling in this place. But obviously that produces a magnetic field. A current of magnets also produces a magnetic field, because when you cause magnets to move, that doesn't get rid of their magnetic field. A current of charges also produces a magnetic field. This is the first concept in chapter 22. If you have a current that produces a magnetic field around it, so therefore the only one of these that does not produce a magnetic field is a static charge. A charge that is just standing still does not produce a magnetic field. Once that charge begins to move in a current, that is what produces a magnetic field. All right, so number 8 is the first application of the right-hand rule. A wire carries a current directly into the page. Indicate the arrow that best describes the direction of the magnetic field to the right of the wire. So if you have a current going into the page, that is an X. If you use the right-hand rule, you can see that above the wire, the magnetic field is pointing to the right. To the right of the wire, the magnetic field is pointing down. Below the wire, the magnetic field is pointing to the left. And to the left of the wire, the magnetic field is pointing up. So above to the right down, below to the left, and to the left up. That is the application of the right-hand rule, clearly indicating that in this case, the answer is going to be B. Again, if the current is going into the page, the right-hand rule tells us that to the right, over here, the magnetic field is going to be pointing down. An electron moving at a blank angle to the magnetic field will experience no force acting on it. So this is an application of F equals QVB sine theta. So the place where F equals 0 is going to be where sine theta equals 0. Sine theta equals 0 when theta equals 180 degrees. Conceptually speaking, the way you know this is that whenever the charge is moving either with the magnetic field or directly against the magnetic field, there is no charge on it because sine of 0 equals 0 and sine of 180 equals 0. A particle moving perpendicular to a magnetic field will experience a magnetic force, will experience magnetic force only if it's negatively charged, will always experience magnetic force regardless of charge, which is magnetic force if it contains any amount of charge. None of the above statements are true. So the answer is C. It does not need to be negatively charged, but it does need to have some amount of charge. Again, if you look at F equals QVB sine theta, if Q equals 0, then F is going to be 0. So therefore, it needs to have any amount of charge, even if that, but it can't have 0 charge. Any amount of charge means any amount that's not 0, because 0 is not an amount. I want to clarify that, just in case anyone gets confused by that. 0 is not an amount. Moving on, number 11. The currents in 3 parallel wires X, Y, and Z each have a magnitude I and are in directions shown below. Wire Y is closer to wire X than wire Z. The magnetic field on wire Y is what? So this again is an application of the right-hand rule. We need to find the magnetic field generated by wire Z on wire Y. We need to find the magnetic field generated by wire X on wire Y. If they are going in the same direction, then that is the direction of the magnetic field. If they are going in opposite directions, we need to figure out which one is stronger, and that is going to indicate the direction of the net magnetic field. So if we just focus on the magnetic field generated by wire Z, the application of the right-hand rule tells us that from wire Z to the left of it, the magnetic field is pointing out of the board. And to the right of wire Z, the magnetic field is pointing into the board. If you look at wire X, the opposite is true. To the left of it, the magnetic field is pointing into the board. And to the right of it, the magnetic field is pointing out of the board. Which means that since wire Y is to the right of wire X, the magnetic field from wire X is going to be pointing out of the board. Since wire Y is to the left of wire Z, that means the magnetic field from wire Z is also going to be pointing out of the board. So wire Z is generating a magnetic field out of the board at wire Y. Wire X is generating a magnetic field out of the board at wire Y, which means that the net magnetic field at wire Y is going to be directed out of the page, or board in this particular case. Moving on. A proton is moving left in a magnetic field directed up. Just to clarify, left is always, if you take an arrow, if you take a pen, you draw an arrow to the left, that is always going to be to the left. This is our V. The magnetic field is directed up. This is our B. It's an up arrow. It's not this direction. Because if your page is over here, then this direction is out of the page. Up is if you draw an up arrow on your piece of paper. Clarifying that. What is the direction of the force acting on the proton? This is right-hand rule number 2. Right-hand rule number 2 tells us to take your left hand and you take your thumb, you stick in the direction of V. You take your fingers and you stick in the direction of B. Since this is a proton, that means it is positively charged. Protons are positively charged, which means we are using our right hand. If it was an electron, we would be using our left hand. So if you stick your thumb in the direction of V and your fingers in the direction of B, the force in question is coming out of your palm. That force is directed into the page. That is E. That is the correct answer. Number 13 is an electron. So now we are using our left hand because electrons are negatively charged. So this time, the magnetic field is directed into the page. So that is an X. And V is down. So the electron is moving down. So this is B, and this is V. So thumb in the direction of V, fingers in the direction of B. Using our left hand, because this is an electron. As a result, the force in question is coming out of our palm and is going to be directed to the left. That brings us to an end of the multiple choice.